So for today's colloquium, we have the pleasure of welcoming Samuel Grushevsky from Stony Brook, who's going to tell us about degenerations of Riemann surfaces together with a meromorphic differential.
So thank you very much. Thank you to the organizers for inviting me here. It's a pleasure to see people I know and to meet new people who I don't know. And thank you to all for coming. So everything I say today will be about the life over complex numbers. I know no other fields, and no other field will be used. Everything I say will be complex. I will inadvertently, I'm sure, mix up algebraic and complex language. So whenever I say curve, I would mean a smooth, complex curve, meaning an algebraic curve, always compact, which is the same as saying a Riemann surface. And G will be the genus of a Riemann surface or of a complex curve. And if you think about this, these are some of the most natural geometric objects. A one-dimensional complex manifold, a one-dimensional compact complex manifold. And you would like to understand goals of study, not of what I'm going to talk about, of studying curves, is sort of understand the geometry of an individual curve or maybe of a general curve. The word general here requires some kind of explanation, which will show up in a second. But here is a model question. This is not the question I'd like to be concerned with, but this is a motivational question that I'd like to use for motivation. So a model question is the following. Could be the following. Does a general, whatever general means, genus G curve have a degree D complex line bundle L, let's call it curve X from now on, and the line bundle is a line bundle over X, such that the dimension of the space of sections is R plus 1 for some R. So given G, D, R. So you have a triple of integers, and you're asking whether a generic curve of genus G have a degree D line bundle with R sections. It's more traditional to say R plus 1, never mind why. Okay? Is this okay? If I should define anything, I'm very happy to do so. I'm very happy to slow down. I'm less happy to speed up, but I could also do that if need be.
Since for giving R, why don't we just write R instead of R plus 1?
Because if you ever read any single paper in the literature, it will be R plus 1. Right? And such line bundles are usually denoted G, GRD, and this means what I just wrote, and not with R plus 1. But anyway, I didn't want to think about that. So this is a question that you may or may not care about. Let me try to convince you that if you ever want to understand anything about curves, you may want to care about such kinds of questions. Because how do you understand the curve? So suppose I come to you and say, hello, my name is Sam, and here is my favorite genus 17 curve. And I'll write down the equations of it for you. This is probably not going to make you very happy. Because if I give you a genus 17 curve, I'll have to write down tons of equations. They'll be high degree, and you will not really know much about this curve. You may prefer for me to come and give you my favorite curve together with some extra geometric data. How it is naturally embedded somewhere, structure of differentials on it, or whatnot. I'm being purposefully vague. I don't want to be more precise because I'm trying to motivate things, not to prove things here at the moment. And then this is the kind of data you would like, because if I tell you that here is my favorite curve X, and it has a line bundle of degree 3 with 4 sections, this is already something, because you know that if you have sections, you can define a map from your curve to a projective space by taking ratios of these sections. And this is a better understanding of a curve. So you would like to understand such questions. Maybe you don't really want to understand them for a generic curve. Maybe you want to understand them for every curve. But this is going to be much harder. So what does generic mean? Generic means the following. So let Mg be the moduli space of genus G Riemann surfaces. So again, I'm using the words Riemann surfaces and curves interchangeably, up to biholomorphisms. So genus G curves up to algebraic isomorphisms. This is a space. I just wrote down a definition of a set. Okay? This is not yet a definition of anything, but there is a key observation. Claim is Mg has a complex structure. This is a slight cheat. I mean, it's not really a manifold, it's a complex orbifold. So this means that locally a chart is not just a copy of Cn, but maybe a Cn quotient by some finite group. This is what you have here. This is a deep statement, which I won't indicate the proof of, but let me try to indicate how it relates to this. So then your question is, so this question here is the following question. So given a general X in Mg, so a class, the equivalence class of X, and then you start asking your question, right? So given a generic curve means to take a general point here. Now the notion of a general point of a manifold of a variety makes somewhat more sense. So you can try to just perturb it randomly. You take an arbitrary point, you have local coordinates, and then you choose a point nearby with generic enough local coordinates. You just throw in a bunch of random numbers for your local coordinates. This is what a generic point could mean. If you're thinking algebra geometrically, this is a generic point of a stack, but scheme, variety, never mind what these words mean. But this is what it means. So the question you would like to understand is, given a general curve, so a curve such that in the parameter space of curves it has generic enough coordinates, does it have whatever properties you want to impose? And you try to think how you would approach this. So the problem is, if I tell you about a generic curve, it's unlikely that I will be able to write it down, because what does it mean generic? It means its coordinates are ugly, right? They're general numbers, they're not rational, they're not real, they're not anything. So this probably means it will be hard for me to actually write down explicitly what I think a general curve is. There are many sufficiently general curves. So one approach to these questions, one approach, not the only approach, is specialization. What I mean by this is you choose some nice X node, which is some particular Riemann surface maybe you like a lot, which you can understand geometrically, of some geometric origin maybe, of some natural, whatever natural may mean, geometric origin. And check your property, this property, say, for X naught. Okay? Then maybe you can argue that the property, whatever it is that you are going to check, this property, for example, is an open property on Mg, which is to say that if it holds for some curve, then it holds for any nearby curve. Any small deformation. X naught. If you can do this, you will have answered your question. So this is a specialization in the sense that instead of working with a general curve, you have decided to work with a special curve. And then you need to argue that the property you have is open. So let's look at this particular property that I wrote down here. The property of having a line bundle of degree d with r plus 1 sections. Let's think whether the property of having such a line bundle is open or not. So suppose I have a curve that comes with a line bundle that has some special property. And then I perturb the curve a little bit. It looks like the line bundle can easily disappear, right? Because the existence of a line bundle means there is something needs to match somewhere. So the existence of a line bundle starts to sound like a closed condition, because you go to some universal cover, you write down the transformation formula for whatever your line bundle is, you think about it somehow. So this is a closed condition, which means that the opposite of this is open. So it means if you know that on some curve of genus G, there does not exist a degree d line bundle with whatever number of sections it is, then you will know that it does not exist for nearby curves. Okay? This is actually true. I don't want to formally prove this, but this is the kind of thinking you may do. If you have some other property of curves you want to think about, oftentimes this property is either closed or open. And for open properties, you can use a specialization procedure. Instead of thinking of a generic point, you pick out one point, and you say that some property holds for this one point, and then it must hold for every point in a small enough neighborhood. Okay? The properties you pick should be chosen carefully. If there is some kind of rationality property, this is neither closed nor open, so you don't want to do that. But this kind of existence of objects is usually a closed property. Okay? So this is a useful technique to study such questions. As a difficulty, it's very hard to have an x naught to choose a curve x naught that is sufficiently general. So you see, this procedure says that you're supposed to choose explicitly some curve x naught. And how are you going to do it? Presumably you're going to use some nice geometric construction to construct this curve. But then if you have done that, the curve is probably very special because it arises from some very natural construction, and you have no reason to expect that every curve arises from that geometric construction. So suppose now that I want to prove that on curves of genus something, there does not generically exist a line bundle of degree d with r plus 1 sections. Suppose I pick one particular curve that I like very much, and suppose it happens that on that particular curve such a line bundle exists. Then I'm immediately stuck. I can deduce nothing. The specialization works well for open properties, does not work for closed properties. So this does not work. And this is indeed a problem. This problem, by the way, is not a random problem that I wrote. It's one of the central questions in the field. Various questions about this, not the existence, but a somewhat more detailed question, are still open. And this is the basic question of the Brill-Noether theory, which goes back a good 150 years, depending on how you count. This is no. So the answer to this question, for which G, R, and D this exists in a generic curve, is known. But if you want to compute the dimension of the space of such, this is already getting interesting, and any questions about special curves become very interesting. So what can you do if you cannot construct a sufficiently general smooth curve? So the second and another approach is degeneration. So what you do then is you change your problem. So instead of considering the moduli space of genus G Riemann surfaces of smooth curves, you allow your curves to degenerate. And the basic theorem in this is a theorem of Deligne and Mumford. In 1969. which says there exists an irreducible, so not a union of components, algebraic stack, orbifold, complex orbifold, mg bar, which contains, which is compact, contains mg as a dense open set, and parameterizes what are known as nodal curves. And parameterizes nodal curves. So what is a nodal curve? It's a Riemann surface with nodes. So you can draw them, say, like this. Okay? So this means locally, near such a point, this looks like xy is equal to 0 in C2. So this is locally two complex planes intersecting in one point. My drawing skills are insufficient to draw a four-dimensional picture, so you should imagine that these two things do not touch. This is one example of a nodal curve. Another example could be, say, this, where the node is here. So it could, the node could either separate your Riemann surface into a bunch of components, or it could fail to separate. It could be an irreducible curve, for example. So the nodes may not separate. How do you think of these objects? Well, you think of this as a collection of its components, which are individual smooth Riemann surfaces that are going to be attached at nodes, right? So if you think of this, this is obtained from two tori which are attached to each other at one point. Okay? So how do you encode this data? So the combinatorics of a nodal curve is encoded by a dual graph. So what does it mean that I have a dual graph? So a vertex V corresponds to an irreducible component. So one of the components, and an edge E corresponds to a node. So for example, if I look at this nodal curve here, there are two irreducible components, and there is one node, and this node connects these two components. So this is a dual graph of this curve. This object here has only one irreducible component, right? And it has one node which connects the component to itself. So it's a loop in the graph. Okay? Let me try to label things a bit more, because this notation will show up in what we do later. So let me call the vertices V1 and V2. Let me call the edge E. And then I would like to label this component as XV1, this component as XV2, and this node will be QE. Okay. So the dual graph of a nodal curve again has vertices corresponding to components, irreducible components of the nodal curve, to the pieces if you cut at the nodes, and edges corresponding to nodes. And edge connects the two components that you see on the two sides of the node. And the fact that taken the parameter space for this, so mg bar is moduli of, I have to say the word stable, but I don't want to think about this, nodal curves up to biholomorphisms. Okay. And then the idea is you can specialize to a nodal curve. So the specialization was the idea that you could approach the question about a generic curve by specializing to some curve, to some particular curve. But the fact that you now have a very nice parameter space for curves, including nodal curves, means you can specialize to a nodal curve. Why would you think this is better? Well, you would probably think naively that this may be worse. I started from smooth objects, and then I decided to specialize to non-smooth objects. But this is not the case, because you see, if I do this, the genera of the pieces are smaller. So in particular, I could take my Riemann surface and I could start breaking it into lower genus Riemann surfaces. And if I keep going for a long time, I'll just break it, for example, into a collection of spheres attached to a bunch of nodes. And then sort of the data becomes completely combinatorial. The geometry gets destroyed. And you may hope that with some luck, you will then be able to handle the combinatorics. Okay. You can hope to handle the combinatorics. And this is indeed what happens. So for the original problem I tried to write as motivation on the blackboard, indeed the first approaches to this problem are via degeneration. I won't review for them how they work, but trust me, there are some very famous and very nice results. There are many difficulties if you want to go down that path, and the difficulties amount to a nice year-long course in algebraic geometry if you were to teach it properly. Because if you think of degenerations, you have a line bundle in the Riemann surface, and now you went to a nodal Riemann surface. And I know what it means to have a line bundle in a manifold. We should first discuss what it means to have a line bundle on a nodal Riemann surface. It's no longer a manifold, it's singular. And there are various issues you have to think. Then the issue of degree, what kind of sections you take, all of this need to be correctly interpreted, but they have been mostly correctly interpreted. So this approach has turned out to be extremely powerful, and the developments of the moduli theory of curves from 1850s, 1880s, from the Italian school to the modern day, are to a very large extent accounted for by the development of the specialization and degeneration techniques in working with moduli. Okay? So this is the end of a strictly motivational part. So there'll be the second motivational piece, but which will bring me closer to where I actually want to be. What questions could I answer now?
Sorry, I missed what you said about stable. What does it mean for?
I never said what stable means. So stable really means that if you look at all the irreducible components, none of them should be a sphere, a Riemann sphere, with 3 nodes. And none of them should be a torus with no marked point. This stability generalizes to all the notions of stability you have ever seen. But I wanted to ignore this because this is not important for me here. Okay? Anything else I could hope to answer? Okay. This is a wonderful subject. You should take a nice year-long course on this at some point. But I wanted to go somewhere further. So I wanted to motivate the results that I actually wanted to talk about. And I did not want to talk about how Delaney and Mumford did their job 50 years ago and became famous for various things. Not just this, of course. Okay? But the question that I'd like to study is geometry of a Riemann surface together with a differential on it. Okay? Let me try to motivate why you'd care about this. There are many reasons. For today, I would like to give one motivation. If you ask me later, there are more. Motivation, well, number 1, even though number 2 will not appear on the blackboard, there are some intersection theoretic computations. So X is my Riemann surface curve, and I'll write omega to be, for the purposes of this talk, will be a holomorphic one form on X. In principle, you can do meromorphic one forms, you can do higher order differentials, but the technicalities appear, and for the purposes of a colloquium, they certainly don't appear. Suppose you have this, then there is a well-known GL2R action on the moduli of pairs x omega. How do you do that? So there are two viewpoints on this. So here is my x, and I have omega which lives on it, right? Take a point on my Riemann surface. So locally, I can choose a coordinate z such that omega is dz. I can always do this away from the zeros of omega. At the zeros of omega I can't, but let's ignore this for the time being. And then, if I have an element gamma in GL2R, acts on z, which I think of as lying in C, which is R2. And so then if I take d of gamma z, this is no longer holomorphic. It's not holomorphic on X. Right? Because what is action? So I have taken an arbitrary real linear map on C. This, of course, does not preserve complex structure. So I could take and stretch the real dimension by a factor of 5 and do nothing with the imaginary direction. This is not conformal, so it certainly does not preserve complex structure. So this is not holomorphic on X, but there exists, in fact, unique complex structure, different in general.
What's D?
Differential. So this is so I still have X, right? So this is an element in H1 XR, if you wish, right? And X I can think of as a smooth surface. So this is a well-defined topological space. This is a differential of a smooth function. And I claim that there exists a unique complex structure.
Should be H1 C.
C, of course, I'm sorry. There exists a unique complex structure on X in which d of gamma z is holomorphic. Okay, and then I let gamma acting on x omega be this x with new complex structure, and this d of gamma z, which is now again a pair of a Riemann surface and a holomorphic one form, because I have chosen a complex structure so that this is holomorphic. What's the complex structure? Well, I mean, you just declare gamma z to be a local holomorphic coordinate. Then you have to check that this matches globally. This is one viewpoint. If you didn't like it for some reason, you're not alone. But this is a preferable, perhaps, viewpoint. Equivalently, so this is the second viewpoint, you write omega, you take gamma, and you act by gamma on the real part of omega and the imaginary part of omega, right? And this is a new form. This is what d gamma of z really means. This is a more global picture, right? So you write omega is real part of omega plus I times the imaginary part of omega, and then you treat this as these are real valued now forms, and you can act on a pair of such. So this is a copy of r to some power, and this is another copy of r to some power, right? And there is a conjugation which conjugates from one to the other, I mean harmonic conjugate, whatever you call it, and gamma is an element in GL2R, so you can act on such a pair, and this is what you do. Alternatively, this is maybe the third viewpoint. So this allows you to see better what is invariant. So given a complex number c, you declare omega plus c omega bar to be the new holomorphic form. The C is related to gamma in some way I don't want to specify. But basically what this action does, all it does is it takes omega and adds to it some multiple of omega bar. And you can see that for this to make sense, there is some non-degeneracy statement. So the imaginary part of C has essentially to be greater than 0 or something like that. So this is actually an action of the upper half plane. Okay. So this is an action, and Teichmüller dynamics is a question of studying this action. So let me try to introduce a little bit more notation. So let omega mg over mg be the so-called Hodge bundle. So what it means is that if you have a Riemann surface X, then the fiber of it will be the space of holomorphic one-forms on X. Okay, so this is a Hodge bundle. So this is a rank G complex vector bundle. So this is just my notation. So this is the space, so an element here is X, so an element in here is a pair X and omega, right? So what I just described is that there is a GL2R action on the total space of the Hodge bundle. Except you should require omega to not be identically 0. Because I cheated throughout. If omega is identically 0, it just completely breaks down. So your form should not be identically 0. So what I defined was actually an action of GL2R on the Hodge bundle with a 0 section removed. So the set of pairs consisting of a Riemann surface and a not identically 0 holomorphic one form.
This unique structure that you get doesn't depend on which omega you pick.
It depends on which omega I pick. So this is an action on the total space of a bundle. So if I have an element gamma here, right? So suppose gamma x omega 1 will be some x prime omega 1 prime, right? And then gamma x omega 2 will be some x double prime omega 2 prime, right? And these have no reason to be the same a priori. Right, because the complex structure will be different. So it's probably easiest to see in this picture, right? So suppose C is, I don't know, 1/2, right? So there is a complex structure in which omega plus 1/2 omega bar is holomorphic. But then omega plus 3/4 of omega bar is not holomorphic in that complex structure. So the resulting complex structure depends on omega. What you can see, of course, is that if you scaled omega by a complex number, that is boring. So that doesn't change things much. So usually you will see people talking not about GL2 action, but SL2 action, because this is good enough. And so Teichmüller dynamics is a study, is a field, is a study of this action. It has many goals. One goal is classify all orbits. And in dynamics, you really should be saying all orbit closures. Okay? So Teichmüller dynamics is a field which just studies this action. And you would think it's a bit weird to have a mathematical field that studies one action on one space. But it turns out to be very rich for dynamics reasons. So for example, understanding this action well allows you to understand everything you ever wanted to understand about billiards. So suppose you have a table in the shape of a polygon with all angles being rational multiples of pi for technical reasons. Understanding the flow of the billiard there is equivalent to some kind of question about this dynamics. So it's not as obscure a dynamical system as you would think.
The trajectory are the dx dy's.
Say it again?
the billiards the trajectory is coming from the
So suppose I have a billiard table that looks like that, right? So, and the billiard looks like this, right? What you do is you're going to unravel this so that as a result you'll get a Riemann surface, and then you're talking about the straight line flow on this Riemann surface. And the straight line on this Riemann surface is very much related to the action of a suitable element in SL2R on the Riemann surface you started from. The translation takes, so let's say the following. Suppose you know for some reason that this action with respect to a suitable measure which you can define, never mind, is ergodic. Then you would know that for almost every direction on every billiard table the flow is uniquely ergodic. It's not bad. You don't need to know properties of SL2R action to prove that, but this is one way to do it.
I'm just wondering that the trajectory is the same as the trajectory of dx and dy.
No. So the trajectory in a billiard is on one Riemann surface, right? So you have one Riemann surface, and you have a billiard, which you then unravel, you get a Riemann surface. So this typical example people draw is perhaps what do we call it, an octagon, right? And then the opposite sides will be identified, and then there'll be a straight line flow. And so it's a flow on a Riemann surface, on a given Riemann surface. But then if you know some properties of the SL2R dynamics on the space of all Riemann surfaces, you will have dynamical results at least on the general Riemann surface. Yeah. This translation is not something I can hope to explain in more detail. But we're still in the motivational phase, by the way.
It seems that instead of choosing one-dimensional space of forms, you could choose a k-dimensional space of forms and
you could.
alternate with the appropriate geo.
How would you do that? So suppose I have a pair of forms. Yeah, so I mean, this is, of course, I could state it in terms of variations of Hodge structures. And I'm not saying this because this is supposed to be as elementary as I can make it. But suppose I have a pair of forms, right? And I take one and the other one, and I stretch them differently. So this tells me that I will not be able to find the complex structure where both of the stretched forms are simultaneously holomorphic. So this is really something deep, because it keeps track in some obscure way of the variation of complex structure, of the variation of Hodge structure, right? So if I have a pair of forms and I apply this, I will be able to choose a complex structure where one of them is holomorphic, but not necessarily two. So it doesn't seem, I'm unaware of any generalizations in that direction. Okay? So this was a second motivational piece, and they want a potential approach which has not been used, has not been developed, is the following, is degenerations. Right? Yeah?
So H1s, you're only considering passive?
Yes. Yeah, sure.
You
So-
could write omega 1, 0.
I could, I'd rather not. So this is a nice rank G complex vector bundle, right? So the space of holomorphic sections.
Yeah, but you're saying something when you say GL2 adds on it, right? You're saying there's a statement, right?
But the space of holomorphic forms is G-dimensional. It's not. So there is no difference. If I say a holomorphic form, it's the same as saying an element here. A holomorphic form on the Riemann surface in a given homology class is unique.
Okay.
Mhm.
The other question I wanted to ask is isn't so this action is that's a Teichmüller deformation, right?
It is true that this action, the orbit is a Teichmüller geodesic. Is a geodesic for the Teichmüller metric on the Riemann. The action under the diagonal matrices, which e to the t, e to the minus t, is a geodesic for the Teichmüller metric on the Teichmüller space.
So I think when I've seen this was with the quadratic differential.
This can be generalized to quadratic differentials. So the more general construction is if you start with a quadratic differential, which you locally write as dz quantity squared.
Right.
This you can do exactly the same. Many computations are easier for abelian differentials. The results I'm hoping to state soon apply for quadratic differentials with no particular difficulty, but I'll need to write more, and since I'll run out of time anyway, I won't. So yeah, the full generality of Teichmüller dynamics is quadratic differentials. I'm choosing to only do it for abelian, which are easier and more studied, and easier for me to state.
So is it correct to say if you have a abelian differential, you square it, you get a quadratic differential?
Correct.
And then the action that I've seen is just that.
It's just that, yes. So the action, the GL2R action exists on the total space of the bundle of quadratic differentials, but if you start with a quadratic differential, which is a square of an abelian, it will remain the square of an abelian. There is a general procedure also to go from quadratic differentials to abelian. If you have a quadratic differential on the Riemann surface, you can always take a branched double cover of this Riemann surface where this becomes now an abelian differential, so it's very much related. I have chosen to sweep all of this under the rug, which you didn't let me, but okay. So all of this was motivational, and I'm aware of how much time it took, and I'm not sorry. Okay. So all I wanted to say is that you may want to study the question of degenerations in this situation. There is another situation that I won't even write on the blackboard, but you may want to study degenerations of another motivation is degenerations of meromorphic differentials such that all of their periods are real. And that turns out to have applications for cusps of plane curves and various completely different questions. For the purposes of time, I won't say anything about that except that in that case we have a completely different set of techniques with Igor Krichever and Chaya Norton, who was my student, which provide in fact more information. But I'll state the results here. Okay? So let me now proceed to try to state the rough form of a result. Okay? The result will be to mimic the understanding of mg bar. So I'd like to compactify suitable spaces. So I have to introduce a little bit more notation for that, right? So given a set of integers m1, mn in Z such that the sum of mi is 2g minus 2, let H mu be the set of triples x, z1, zn, omega, such that x is a Riemann surface, omega is a holomorphic one form on this Riemann surface, and such that the divisor of omega, the divisor of omega, is the sum of mi, zi. Okay? So this is a space of triples, and well, tuples, but there is a Riemann surface with a bunch of marked points, distinct, and they're holomorphic one forms which has prescribed zeros and poles at these points. For the purposes of this talk only, let me say that all the multiplicities are positive, so I'm talking about holomorphic differentials. You could do meromorphic. Again, I'm choosing the simplest case to describe here. So this H mu really is a subset of the Hodge bundle, but I also want to record the locations of the n marked points. So this is the space of triples x, z1, zn, omega with no condition. So MGN, this is the moduli space of Riemann surfaces x together with z1, zn, which are points on the Riemann surface, can be compactified to allow nodal curves. And you should require that the points are never coinciding and are never at the nodes. Over this space, there is this Hodge bundle. And the Hodge bundle can also be compactified. And this will be still a rank G complex vector bundle. And I'd like to describe what the fiber is. So given a nodal curve X, what we should call a holomorphic differential on X is a collection of meromorphic differentials, which I'll denote omega v on xv, which remember were the coordinates, the components of the nodal curve, such that their only poles are at the nodes, and they have opposite residues. Okay, I'll do an example in 2 minutes. Question?
Yeah, sorry. So what is the effect of MI? Could you just enter MI? What happens?
Here nothing happens, right? This picture, this is a description of the total space of the Hodge bundle. MIs don't play a role. So the theorem is the description of the closure of this guy. This is called a stratum. It's called a stratum because the GL2R action actually is on that. The GL2R action actually preserves the multiplicities of zeros of holomorphic one forms, as you can see from the local picture. And the theorem that I won't be able to fully state, and this is fine, but I wanted to try to explain what kind of result it is. And this is joint work with Matt Bainbridge in Indiana, with Da-Wei Chen at Boston College, with Contage and Ro, who is currently at Max Planck, and with Martin Möller, who is in Frankfurt, and me is somewhere here, is the following. The closure of a stratum, H mu, in the total space of the Hodge bundle is, okay? These 3 dots will, I'm afraid, stay like that for a while. I'm not sure I'll be able to state exactly what it is. So what we can do is we can say which such things arise as a limit of differentials with prescribed multiplicities of zeros. Okay? And the answer is in terms of some collections of meromorphic differentials, but before trying to explain what kind of requirements go into these 3 dots, let me try to explain rather what the difficulty is in the process. So I'd like to explain the difficulty in the simplest, perhaps non-trivial case. So I'd like to understand, look at the stratum, the closure of the stratum H2 inside omega M21 bar. So what does this mean? Let's unravel the notation. So this is the locus of genus 2 curves. So X is a genus 2 curve, together with one marked point, Z, and the differential omega, such that omega has a double zero, at Z. Right? It's the locus of such curves. For algebraic geometers, this is not an interesting problem because this is a hyperelliptic curve and this is a Weierstrass point on this hyperelliptic curve. By saying these words, you will be able to answer any question you may possibly want about this locus. But the goal now will be to forget that this is a hyperelliptic curve and the Weierstrass point, and I'd like to describe what the general issues are that you have to deal with. So we'd like to understand the boundary of this. So there are different types of nodal curves. So there are some types I specifically wanted to do. So here is one type of degeneration. Okay? So this is a genus 2 curve that I pinched here. I don't know whether you can see the picture. This is supposed to be a smooth genus 2 curve, and then I just pinched it. So I got 2 genus 1 curves, and let's say Z is on the right-hand side. So the dual graph, which we drew, looks like this. So this is, say, 1, this is 2, this is x1, this is x2. I have to indicate the point Z somehow, so I draw a small, what people call a half edge or a leg to indicate that Z sits here. Okay? This is one kind of degeneration. So a holomorphic differential on this thing is omega 1 and omega 2, right? A differential here and a differential here, such that they have at most one simple pole at this point, which is traditionally denoted QE, as I tried to set up the notation straight from the beginning, right? But then omega 1, omega 2 are holomorphic, because by the residue theorem you cannot have just one simple pole. However, if such a point, if we're in the closure of the stratum, the multiplicity of omega 2 at Z certainly has to be at least 2. Because if such a point lies in the closure of the stratum, the multiplicity must be at least 2. Which is to say that omega 2 is just identically 0. Okay? And this is sort of bad news, because we have lost all the information. And this is the stereotypic bad news. So the bad news in all of this are the same, that main difficulty in the limit, we can see that some omega v is just identically 0. So we don't know which points on the corresponding components are limits of zeros. Okay? Let me do 2 more examples. Still we're in this case. So here is another example. Sorry. So this corresponds to the following picture. I have a Riemann surface of genus 0, a sphere with a marked point, and then there are 2 tori here. Right? So let's look at this situation here. So I have, omega 1 here, omega 2, and omega 3. Omega 2 may have 2 simple poles. At these 2 points, of course. However, let's call this one QE. However, the residue at QE of omega 2 must be equal to minus the residue of, say, omega 1. But omega 1 is holomorphic. So this means also omega 2 is holomorphic, which means omega 2 is identically 0. As before, right? So in this case, I have 3 components. On the middle component, a priori, you would think you can have 2 simple poles, but the residues must match, must be opposite to the other side. On this side, there is only 1 potential simple pole, so it's not there. So this guy is again holomorphic, but there are just no holomorphic differentials on a P1 whatsoever. So this is bad. This is stable. This is stable because this is an elliptic curve with one node. This is okay. And this is a P1 with 3 points, right? Because there is one marked point. So this is stable. Yes, I was not going to say that. But
I'm just wondering, do you want to allow variable? I mean, do you want to allow variable?
I still have 1 minute, so let me do one last example. Yeah, I mean, yes. So here is one more example. So this is when you have two components that intersect in two nodes. And then the top thing should have genus 1, otherwise this is not stable. Okay? And then you look at this thing here. So suppose this is omega 1, this is omega 2, right? And then there are 2 points Q1 and Q2 here. And then you see that the multiplicity at Z of omega 2 must be 2. Multiplicity at Qi of omega 2 must be at least -1. There are at most simple poles here. But this is again impossible. So omega 2 is still identically 0, even though a priori the residues could be non-zero. But this is a P1, this is a Riemann sphere. So you cannot have, so the differential ZD0 in the Riemann sphere has two simple poles and doesn't, whatever, doesn't work out. Okay, so it still must be 0. Okay, because the degree is off. I mean, the degree should be -2, but it's not. So in all of these cases, the differential is just identically 0 on the component where your marked point lies. So this means you have recovered no information by just looking at the limit. So what you should do is, a solution is you rescale omega on each component to make it non-zero. And then you get a collection of meromorphic differentials with high order poles. So what the theorem should say is that a point lies on the closure of a stratum if and only if you can choose a collection of differentials on the irreducible components with higher order poles that satisfy a bunch of conditions. And some of these conditions are very easy to see, that the orders of poles must match. At each pole, the sum of the at each node, the sum of the two orders of the pole must be -2. That if on both sides you have a simple pole, the residues must be opposite. Then there is some kind of orientation. You know which components are smaller, which are bigger. So this will tell you where you have a 0, where you have a pole at a node. And this were all reasonably well understood, even though not stated this way in Teichmüller theory community and then in algebraic geometry community. But then there is one last condition which nobody saw, and this is some condition on residues. So there is some complicated condition that says you have this collection of meromorphic differentials with higher order poles, and the higher order pole may also have a residue, remember. So there is some condition that says basically the sum of the residues on one level is always 0.
What is it? I mean, the last sentence on this. Some of the residue are
At the sum, so you'll order your components by size, say. And then basically the residue condition says that the sum of all the residues of all the differential at poles of the same size is 0. Okay. And these are the conditions you can write down. It's not so bad. And basically, as you write them down, I would also be able to convince you that they are necessary, because I'll be able to tell you how you see that they are preserved if I rescale things. What I would not be able to tell you in another 20 minutes, which I'm not going to take, is why the conditions would be sufficient. And that requires some kind of plumbing techniques or some flat geometric deformations. Okay, so the main result is basically we know the closure of a stratum in this compactification. And this is, you can read it on the archive, enjoy all the 60 pages of proofs and pictures and whatnot. What you won't read on the archive is that this is not necessarily the best compactification you'd like, because it's singular. And of course, you'd like to have a smooth complexification, smooth as a stack with simple normal crossing boundary dividers, which represents the moduli functor. This is not yet done, but there is another 100 pages that we have that solves some of these problems, but this is not, we're not finished yet. Okay. Sorry about going over time.
Any questions?
Could you write out one example, just two components? So curve given two components. Could you write out one?
Let's do these examples,
Okay.
if you don't mind. So in this example here, so your differential became identically 0 on this side. That you don't like. So what you do is, in this case, you'll have omega 1 will be holomorphic, and omega 2 will have a double pole. I mean, not omega 2, the scaled omega 2. I'll denote it eta 2. So the scaled omega 2 will have a double pole at the node. Okay? And this is possible. And then you will see that the differential omega 2 will have a double pole here and a double zero here. And this is only possible in an elliptic curve by the Abel theorem if twice that point is twice that point. So it means this is only possible if the difference of these points is a two torsion point on the elliptic curve. So this tells you that the intersection of the closure with this consists of the locus where the difference of these 2 points is a two torsion point on the elliptic curve, which is good because you didn't want all of this locus to be in the boundary, because you have something which is of co-dimension 1, and the boundary should not contain something which is of the same dimension as the thing. Here, again, you will rescale and the object.
What's the form on the elliptic curve? No V part.
Here is just dz.
Just easy, right?
So here it's dz, and here it's a form that has a double pole here. I mean, dz on a torus has no zeros, no poles. It's a holomorphic form. So here it will be a holomorphic form, no zeros, no poles. Here it will be a meromorphic form with a double pole and a double zero. In this situation here, again, on the two tora, you'll have holomorphic forms, no zero, no poles. And on this component, you'll have double poles at these 2 points and the double zero here, which is perfectly possible on P1. In this situation, it gets, and it's the same. So it's dz here. And again, a form with two double poles and one double zero, but there are some issues, so I don't want to go there. So the issue is the residue condition is different here and here. So the residue condition here, sorry, let me correct what I said. So here, the form upstairs is just dz, and down below you have a form on Riemann sphere with two double poles and a double zero. And this form on a P1, if you write a form that has a double zero at 0 and double poles at two other points, it must have residues at these two other points. You can check this. Here, our residue condition will tell you that the residues must be 0. So this is not possible. So it means that the closure of this intersect this locus is empty. Right? So sorry, that's what I meant to say. So the residue condition rules out this, allows this.
How can this space be compact if you do not allow the points to collide?
If the points so this is a question about the Lin-Mumford complexification of MGN, really. So if the points collide, you just bubble off an extra P1. Right? So this is the situation. So this is a situation where this point here wanted to collide with two nodes. Well, with one node. Right? But then you just bubble off a P1 and put the points there. And then you keep doing this until all the points have separated. This is part of the beauty of the Lin-Mumford theory. Since I cheated about MGN because I didn't talk about the points, that's how it's taken care of.
Any other questions? All right, let's thanks again.